Welcome to Module 6, and this is the first lecture of this module. In this module, we are going to discuss on condensation and boiling heat transfer, condensation and boiling heat transfer. From the name itself, we can understand that these two phenomena, there are two different phenomena, one is condensation, another is boiling. These two phenomena that do take place in some situations when the heat transfer also takes place, and these phenomena, both the phenomena are related to some phase change operations. Phase change phenomena, and we are in this lecture going to discuss on condensation heat transfer first. And from the name itself, we can understand the condensation is the change of phase from vapor to liquid. So, condensation, if we define, is defined as the changes or change of phase from the vapor to the liquid. So, we are going to have couple of lectures on this condensation heat transfer. Now, what happens, we know that when a liquid boils, then we can say that the liquid is a saturated liquid, and at the same time when it is boiling, there is a vapor. At that boiling point, there will be a vapor generated, and that vapor will be a saturated vapor. And so, when we do reduce the temperature of the saturated vapor, it has no other option except condensing. So, it is converted from vapor phase to the liquid phase. So, this is the change of phase that or phase change that takes place during condensation phenomena. And we know that condensation is a very commonly used operation, particularly for chemical engineers for heat transfer. Okay. So, condensation is applied, you know, all know, if we have already studied about this mass transfer. In the mass transfer, there is a distillation column, and in the distillation column, all the distillation column are usually associated with a condenser. So, if I say about that application of condensation, what you can understand, condensation heat transfer. As I told you that the first thing can be considered as the distillation column. And if we have already known about this, distillation column that is being used for a mass transfer operation is the separation of components from a liquid. The mixture of components are there in a liquid, and this can be separated with the help of distillation. And in the top, there will be some vapor which will be coming out at the top, and at the top there is a condenser that is being placed. That vapor is condensed into liquid form, and part of that liquid can be taken as a product, that is called distillate, and part of the product can be entered into the distillation column itself, and which is called as the recycle or reflux ratio or reflux, whatever you say. So, this is one typical example. Similarly, there are many issues, like for example, if you consider about a reactor. From a reactor, we can have some vapor that is coming out after the reaction, because many reactors that do operate at a very high temperature, the reactions are usually takes place at high temperature, and then in that case the product can come out in the form of vapor phase. But if we have to recover the product in the form of liquid, then what we have to do? We have to pass it pass the vapor through a condenser. So, in this case also we can understand that this is nothing but a condensation phenomena that is being taking place, and then heat transfer phenomena is being taking place. So, what is the idea behind this is condensation is that from the vapor phase we are extracting that extra energy, and which is in the form of latent heat. So, we are taking out the latent heat and just reducing this phase from vapor phase to the changing the phase from the vapor to the liquid phase, where it is losing the extra energy, or which is the latent heat of vaporization that is being lost by this fluid. So, this is what is being done through condensation operation. Sometimes it is being soft cooling is also being done during condensation operation. Soft cooling means we can understand that it is not at the temperature of the saturation condition. The vapor, after it is condensed, it is first condensed into a saturation temperature condition in the form of a liquid. So, saturated vapor is converted into a saturated liquid, and then after that this saturated liquid can be further subcooled. Its temperature can be further reduced by putting a coolant. So, that is called soft cooling operation. So, soft cooling is we can say is a side by side operation which takes place after the condensation operation at saturation point, or at bubble point, or at condensation point, whatever we can say. Similarly, there are cases like we know that boiling in case of heat exchangers. We will discuss little later about this in some subsequent lectures. We will see about heat exchangers which are used. This is to use, suppose boiling a liquid or heating a liquid, that is can be done by this kind of things can be done by steam heating. So, when we are doing in the heat exchangers, we are trying to heat a liquid, warm a liquid or boil a liquid, and that is done by steam. So, it is called steam heating. Under that situation, we can do that the steam is being passed onto the surface, and this steam gets condensed onto the surface of the outer surface of the tube, say, and in the inner surface there could be some other fluid, which is the cold fluid that is going in, and the cold fluid can boil, or cold fluid can have elevated temperature due to the condensation. The boiling is possible, either this cold fluid can be of higher volatility. So, its boiling point will be less compared to the boiling point boiling point of water, so that this is possible, or otherwise the steam can be placed at a very high pressure. So, high pressure steam means that the boiling point of water at high pressure will be high, and then that high pressure steam can also be used to boil some liquid or water even at lower pressure conditions. Okay. So, these are the typical examples of condensation operations, and it is widely used, and it has got a lot of practical and industrial applications for condensation operations. Okay. Now, when we try to see that how this condensation takes place, then there are certain things comes to our mind, that first of all, if we just try to classify condensation, we can classify like this way: condensation. So, this we can classify first into two parts. First one, we will say that homogeneous condensation, and another one we will say that surface condensation. Okay. Now, homogeneous condensation means here what happens, that suppose we have a mixture of vapor or gas, which is now cooled. So, once it is being cooled to some temperature, so some of the vapors that may condense at that temperature, or some of the vapor components of the gas mixture may condense at that particular temperature. So, then what we will find? We will find that fine or minute droplets of a liquid which will be suspended in the carrier gas. So, that is the situation that is called homogeneous condensation. So, we can say that minute droplets suspended in carrier gas when cooled. So, this is the condition. Condition is that suppose I have a mixture of vapor or gas with some vapor, and I am trying to cool it. So, it may be possible that some part of the vapor which may condense and give us some minute or fine droplets of that particular component, and then we call it to be a homogeneous condensation. And then another one is it's happening on the surface. So, if a vapor or gas mixture, if a gas vapor mixture or a vapor comes in contact with a cold surface, then what will happen? Then condensation takes place on the surface. So, we have a surface and a vapor or a gas vapor mixture, whatever it is, that comes in contact with the solid surface and which is at lower temperatures, which is a cold surface, and then the vapor gets cooled down and it loses its energy in the form of latent heat, and then it condenses on the surface. Now, this condensation, which is of more importance to us, because in the heat transfer situations we usually do go by the surface condensation methods, and in this surface condensation again can be divided into two parts. One is called film condensation, and another is called dropwise condensation. If I write like this, sorry, dropwise condensation. So, the difference between these two is, one is film time condensation. We can understand that there is a surface, and when the vapor comes, gets into contact with the cold surface, and it makes a film over the whole surface. So, the condensate comes out in the form of a film over the surface. So, this is called film condensation, and the dropwise condensation means the condensate is formed in the form of drops. So, here there will be film of condensate Condensate means is the liquid after condensation, and here drop of condensate. So, in this case a blanket you can say that the liquid cover the surface like a blanket, okay. But in this case drops are formed at different locations, okay. Now, what happens is, in this case the liquid, if it is if there is a gravity flow, then liquid, if it is a vertical plate, then liquid once it is condensed, it is formed, and then it will gradually with the force of gravity it will come down and it will drain out, and the layer will continually exit, and as we go down, in case of vertical plate, as we go down, the thickness of the condensate film will go on increasing. But in case of dropwise condensation, what happens? The drops are being formed at different locations of the surface, and then what happens, that drops grows, okay, and after certain the size of the drop, this gets detached from the surface and fell down, and the new drops comes. So, new drops, so there will be simultaneously there will be some amount of free space at the surface, and there will be some amount of the space which is covered by the drop in case of dropwise condensation. And therefore, what happens is that dropwise condensation is always preferred. We will come to that, but one thing we should say that film condensation happens for a liquid which can wet the surface. So, when we are considering the condensation of some vapor and the liquid which is formed, if that is able to wet the surface on which it is condensing, then we can say that film type condensation will be formed. And dropwise condensations are it's a very rare situations. It is the cases when the fluid doesn't weigh the surface, but it has been found for a long exposure, long time exposure, even the dropwise condensation behavior gradually or slowly gets converted into a film time condensation behavior. So, but one thing we can understand that between film type and dropwise condensation, if we try to see that film type versus dropwise, if we try to see the merits and demerits of this, that we can understand that film type condensation is a very common, it's difficult to achieve. So, it is difficult to achieve. So, what is being done in this case is we have to put either some coating on the surface or some additives to the vapor to have dropwise condensation. Okay. But to be honest, that this particular dropwise condensation, though these attempts are there, several attempts are being made, but is yet to be successful, for having sustained for a long time, sustained dropwise condensation. Okay. So, we can say then at the same time we can say that in case of film time condensation, heat transfer coefficient is less, because here resistance is more and rate of heat transfer is less, and in this case resistance is less, but and heat transfer rate is high. So, what is this? We can try to understand and we will see this. So, because of that reason, this particular thing is more preferred, but difficult to achieve, as we have said. So, now what we are telling is that, which is the very important thing, is the resistance is more and rate of heat transfer is less in case of film type condensation, whereas in dropwise condensation the resistance is less and heat transfer rate is pretty high. We will see from this, if we try to see that, say these are the cases. So, this is, say these are all. So, this is a saturated vapor, you can say, and this is the liquid. It is a vertical plate, we can say that this is the vertical plate. Okay. Similarly, is the case here. This is a vertical plate, okay, and here, and this is this not only plate, is the cold plate. This is the cold plate, and what is happening is here. So, these are saturated vapor, And what is happening here? Say, consider like this, consider like this, consider like this. So, these are all droplets, drops. So, what is happening? This is the cold plate in both the case. So, we can understand this is film type and this is dropwise. Okay. Now, we can understand that there is a saturated vapor and this surface is cold. As the vapor comes into contact, it goes on condensing and then liquid will flow like a film over this surface and it will gradually come down, and therefore, gradually more and more molecule will come to the bottom, and therefore, that thickness will gradually increase. So, this is the film thickness, okay, and this film thickness will be function of. So, if I say this x, so delta is a function of x, this is the film thickness which is a function of x. But so what we can expect, that there will be a resistance of the film. So, the liquid, the saturated vapor, after in the very first case, then there will be a film formed, and this vapor then cannot come directly to the contact with the solid wall. So, that the heat exchange is not directly with the solid wall. So, the vapor is exchanging heat with the liquid, it is passing through this, the heat is being traversing or through this and then going to this hot cold plate and going to this side. So, heat transport is happening, and in between vapor and the solid wall there is a film of liquid which is acting as a resistance for that. So, this is the extra resistance that take part in the case, but in this case what is happening in case of dropwise condensation, part of the some of the places are being occupied of the surface are being occupied by the this kind of drops. So, there is the small drop, then is a bigger drop, and then finally at some time it will be detached from the surface. So, part of the things like these regions, you can say that vapor is in direct contact with a solid surface. So, a part of this is in contact, the vapor is contact through the liquid, and in part it is in direct contact. So, why it is in direct contact? The heat transfer rate is very fast, and it is because this surface is getting renewed, because the ones that drops are coming out, once the drops are getting detached, so that particular surface is getting renewed, and again it is becoming it will come in contact with the vapor, saturated vapor. So, therefore, always there is an existence of some bare surfaces and some surfaces covered by drops. But in case of film type, it is always being, except the initial condition, is always being covered by a layer of liquid, and therefore, the resistance is more. So, therefore, the resistance is more in case of film type condensation. In dropwise condensation, resistances are less and heat transfer rate is more. If the resistance is less, naturally the heat transfer rate is more in case of dropwise condensation. Okay. Now, this is one most important part of these understandings, and then we will have just little idea about that film coefficient, the approximate range of film coefficient for condensation. In general, what we will say that, as we have discussed earlier also, that dropwise condensation is rare to be achieved. So, and it is difficult to achieve. So, therefore, mostly it is the film-wise condensation or film type condensation or film condensation that will be discussed in most of the situations, and we can say that the approximate range is of film coefficient for condensation. This value is like this, condensation of steam. This is just to get an idea, having some feelings about these values. Condensation of steam dropwise, okay. This is roughly equal to 5,500 to 16,000 in this level watt, to 16,000 in this range in watt per meter square per degree centigrade, and this is for steam, and organic vapor and it is film type, is nearly equal to 1000 to 3000 watt per meter square per degree centigrade, and it is told that these values may be very high for clean surfaces. So, for clean surfaces the values are high. So, typical values, if we try to see again, for organic vapor, it happens to be like 5500 watt per meter square per degree, as high as this much, and for steam and dropwise it is starting from 55,000 to say 4,50,000 watt per meter square per degree centigrade. So, we can understand, we can have, this is just to get an preliminary idea about the kind of heat transfer coefficient, film coefficient also is called, the values we can get, is just to get an idea on this. Now, we are going to, there are many discussions, many researches have been carried out regarding this film type and dropwise condensations. So, what we are trying to do is we will discuss part of these, some of these situations, some of the theories we will try to discuss. To start with, we will know that how the heat transfer coefficient can be obtained in case of film condensation or film type condensation, and this is being analyzed first by Nusselt in 1916. So, we are going to discuss that part, which is the analysis by Nusselt, and that is what we are going to discuss now. Okay. And so, for that we will do it, that film condensation on vertical plate. So, we will see for the vertical plate, film condensation for vertical plate or vertical surface. Let us write vertical surface plate. We will take the plate as a surface. So, how to do this analysis? Let us see that. And this is the, this analysis has been done by Nusselt first. It's done by in 1960. Okay. Now, what we will do is, so this is say so vertical plate, and this is coming in x direction. If I say that this is the y direction, and what is happening is, say this is the saturated vapor, condensation of the saturated vapor we are discussing, and here the film that is being formed. Okay. And say at any distance y, okay, right. So, we will take that this is at any distance y, this distance is y, and this is dx. So, this is becoming the volume element. We will take the breadth of the plate is equal to, or width of the plate is equal to 1. Okay. It is like this. So, this will be taken, so that like the film will look like this. This will take as unity. Just see the enlarged view of this particular volume element. It will look like this. Okay. Now, here this is dx, and this part is basically delta minus y, the total is delta, and this actually, though I have drawn it like this, should be this won't be this much. So, this will be negligible with respect to this. We will take this to be like this much. It will be like this. So, this is negligible because it is an enlarged view, and what is happening here, the force acting upward on this element, fluid element, there are fluid element is the condensate material, it is a liquid material. There are some forces acting. One force is acting upward, that is the drag force, and this drag force is a viscous drag, and this is basically mu into del Vx by del y into dx, and as I told you, this dx into this width is unity, that be giving the surface area. So, dx into unity is the surface area. This drag force is acting on that surface. Okay. And here we have some forces which are like rho L g into delta minus y, delta minus y into dx, and this is another force. So, this force is nothing but we can understand rho L g into delta minus y into dx. This is nothing but that weight of the liquid, okay, that is trying to come down, and here we will have rho v, okay, and then g into delta minus y again into dx. So, this is becoming this is weight of the vapor. So, it is the buoyancy force, basically it is the weight of the vapors that is acting upward, and this is the weight of the liquid that is acting downward, and we can see here that this is delta minus y into dx into unit width is becoming the volume, into rho is becoming the density, and becoming the mass, and into g is the weight, and this weight is nothing but the weight of the vapor if the place was occupied by the vapor. Therefore, if we do the balances, we will get a balanced equations like this. So, weight of the liquid is balanced by viscous shear force and the buoyancy force due to the displaced vapor. Okay. So, now if we do the force balances, then thus we get what we get is the rho L g into delta minus y into dx, and that is equal to mu L. Now, we will write dvx by dy because velocity is varying along y direction only, we will assume that, into dx plus rho v g delta minus y into dx. So, v indicates, v is the suffix for the vapor and L is the suffix for the liquid. So, we finally get that mu L dvx by dy is equal to into dx equals to this is equal to rho L g delta minus y into dx minus rho v g delta minus y into dx. And then what we get is from there, if we do integrating, after integrating it's like this 0 to Vx dVx is equal to rho L minus rho V by mu into G, and here 0 to y we have delta minus y dy, and this gives so Vx is equal to rho L minus rho V into G by mu into delta y minus y square by 2. So, this is the equation that we are going to get about the velocity profile. So, this becomes the velocity profile of the fluid stream that is coming down. after getting condensed. But while doing this derivation for the velocity profile, we have taken certain assumptions. So, what are the assumptions that we have taken? Let us try to understand that. Assumptions what we have taken are, first of all, the flow of the condensate film is a fully developed laminar flow. Then we can have that interfacial shear between the vapor and the condensate film is negligible. So, interfacial shear force between the condensate and the vapor is negligible. Then we have liquid properties are constant. Then we have vapor is saturated, already we have discussed. Otherwise, there will be some other kind of energy balance is needed. Vapor is saturated, then heat transfer through the condensate film. So, this some of the things we have not discussed yet, we will be discussing these assumptions, and while we will be trying to find out the values of heat transfer coefficient. So, heat transfer through the condensate condensate film is by conduction mode, and then we have the temperature profile is linear. That is another important assumption. So, anyway, we have these are the assumptions that we are going to take up. Some of the assumptions already we have taken, like that flow is of the condensate fluid is fully developed and that is a laminar flow, and therefore, we have got a velocity profile of that kind, because while we have done this viscous shear drag that is mu into del u by del y and the dvx by dy, it is the Newton's law of viscosity that is being applied. And then interfacial shear force between the condensate and the vapors, that is also we have taken into consideration. If you see here, the meaning of this particular thing is that in this region there is no shear force exists in this particular region, and then that is the assumptions. And then another assumption is the liquid properties are constants, like some of the liquid properties already we have discussed, like mu L, rho L, density, viscosity. These we have taken as constant. Some more properties we will be discussing, like thermal conductivity and all these in future, those also are being assumed to be constant. And the vapor is saturated, that we will see that, because it is only the condensation heat that is being utilized, that is the latent heat of evaporation is being used for the heat to be transferred. Okay. Now, the other things will be coming in due course of our discussions. Now, if we have got a velocity profile of this kind, then so Vx is equal to rho L minus rho V into G by mu into delta y minus y square by 2. So, this is the velocity profile we have discussed. Now, if you try to find out the mass flow rate of the condensate, per unit breadth of the film at any position x is. How is that? It is nothing but velocity into the area. So, we know the velocity. So, this is the film is coming like this, the film is coming like this. We know the velocity V x, and then we know the surface area. So, this will be give you the flow rate, volumetric flow rate, and then multiply by the rho will giving the mass flow rate. So, this is what you have to do. So, we will find out m dot, this is nothing but 0 to delta, that is the range between 0 to this is 0 here and this is delta, 0 to delta rho L into V x into dy into 1. So, dy is, this is the dy, and 1 is the unit weight and V x is the velocity. So, become dx V x into dy into 1 is become the volumetric flow rate, into rho L is the density of the liquid. So, it is integrated from the whole boundary layer thickness or whole thickness of the film, then it gives us the volumetric flow rate of the condensate. And then if we put the values of V x over here, then it is becoming 0 to delta rho L minus rho V by mu L into G into y delta minus y square by 2 into dy. So, basically this value is coming to be rho L into rho L minus rho V by 3 mu L into G into delta cube, and this delta is equal to local thickness of the condensate film. Okay. Now, once we have got this expression, once we have got the expression for mass flow rate, then if we try to find out the rate of heat transfer, and if we try to find out the values of the heat transfer coefficient, then certain things we have to do. Let us assume that the temperature profile, as we have discussed, is linear. That means T equals to A plus B y, and we know the conditions at y equals to 0, T equals to T w, and at y is equal to delta film thickness, T is equal to T infinity, which is the temperature of saturated vapor. Okay. Under that situation, what happens is, if we put these boundary conditions, we get that T minus T w by T infinity minus T w equals to y by delta. This is the linear velocity profile. So, this is an assumption, and then if we try to find out this expression of del T by del y. So, dt by dy at y equal to 0 comes about, this is becoming T infinity minus T w by delta. Okay. Now, what happens in this case when there is a condensation take place? So, film, one thing we should see here, that if we see the bound diagram, the heat transfer from here, so which is being getting condensed, and that is being transferred through this. So, at steady state conditions, at steady state, we can say that K into dx into 1, that is the area, into dt by dy at y equals to 0, that is equal to the heat transfer by this is equal to that K into dx into T infinity minus T w by delta. That is the heat transferred by conduction mode. Okay. And this I will write K L. K L is the thermal conductivity of the liquid. K L is equal to thermal conductivity of liquid. So, if we know that, then dm dot, that this here I have written like this because dt by, no negative sign has been placed over here, because dt by dy at y equal to 0 is a positive quantity. dt by dy itself is a positive quantity, and therefore, we have not used like Fourier equation, they have got minus k into dx into dt by dy. So, we are not writing minus k because dt by dy itself is a positive quantity. So, there is no point of writing this negative part over here. So, then the change of rate of condensate flow is because of this condensation. Okay. So, dm dot is the change of rate of condensate flow equals to, is happening because of the heat transfer and for that heat transfer rate, that is KL into dx into T infinity minus Tw by delta, and this by latent heat of condensation or latent heat of vaporization. So, this latent heat of vaporization, so this is the amount of heat transferred divided by the latent heat of vaporization. This gives the amount of the condensate that is being formed because of the heat transfer. So, dm dot is the rate of change of, this is the rate of change of heat transfer and divided by latent heat of vaporization or latent heat of condensation. So, what is happening, this much amount of condensate is being formed. So, this condensate, so rate of change of condensation with the distance, if we say this becoming then KL into T infinity minus Tw by delta into LV. Okay. And now, we know m dot is equal to rho L into rho L minus rho V by 3 mu L into G into delta Q. From here, we can say that dm dot by dx equals to rho L into rho L minus rho V by mu L into G into delta square into d delta by dx. So, therefore, if we put this expression and do integration, then we can get 0 to delta, delta Q d delta equals to K L mu L T infinity minus Tw by rho L into rho L minus rho V into G into LV into dx. This is 0 to x, and this gives us that delta equals to 4 mu L K L T infinity minus Tw by rho L minus rho V into rho L into G into LV into x whole to the power 1 by 4. So, then what we get, heat transfer coefficient H x into dx into T infinity minus Tw, that is the by convective heat transfer is equal to the conductive heat transfer will be KL into dx into T infinity minus Tw by delta, and from here we can find out that Hx is equal to KL cube into rho L minus rho V into G into LV by 4 mu L into T infinity minus Tw into x whole to the power 1 by 4. And then what we get is, then nu x is equal to Hx by K L, and that is equal to G LV rho L minus rho V into x cube by 4 mu K L into T infinity minus Tw, and this is whole to the power 1 by 4, and then H bar is equal to 1 by L 0 to L H dx as we know, and this is equal to 4/3 H x is equal to L, and this is happening to be 0.943 G L V rho L into rho L minus rho V into K L cube by 4 mu L into T infinity minus Tw whole to the power 1 by 4, and there will be 1 L. So, mu L and this 4 won't be there. So, this G L V rho L minus rho L into rho L minus rho V into K L cube by mu L capital L T infinity minus T w whole to the power 1 by 4. So, we can understand that all L indicates, suffix L indicates is the property of the liquid, V indicates property of the vapor, and here all properties, all liquid properties to be evaluated at T f, which is equal to T infinity plus T w by 2. Okay. Exactly in the similar fashion, we know that for laminar film condensation on horizontal tubes, Nusselt obtained a relation where H bar is equal to 0.725 into rho L into rho L minus rho V into G into L V into K L thermal conductivity cube by D, in place of L it is D into T infinity minus T w whole to the power 1 by 4, and D is the tube dia. So, this is about the heat transfer convective heat transfer coefficient for average convective heat transfer coefficient for a horizontal tube. Now, I will ask a simple question that under identity, otherwise, so the problem is otherwise under otherwise identical condition, what is the ratio of HL vertical heat transfer coefficient to HH horizontal heat transfer coefficient when a tube is kept as vertical or as inclined conditions. So, we can understand that from these above two relationships whatever we have discussed, we can say that H V average by H H average equals to 0.943 by 0.725 D by L whole to the power 1 by 4, and this happens to be 1.30 into D by L whole to the power 1 by 4. And we can also say that when D equals to 0.35 L, we have H V bar is equal to H H bar. So, these are the this is what we can understand, that normally when a tube is placed in the vertical positions, that heat transfer coefficient is more than compared to the horizontal positions, and at one conditions when D is equal to 0.35 length of the tube, then both vertical heat transfer coefficient, convective heat transfer coefficient and horizontal convective heat transfer coefficient H H bar becomes more or less the same. In otherwise, H V bar by H bar is equal to 1.3 times D by L whole to the power 1 by 4. That is what, based on the Nusselt derivations that we have got. Okay, I will stop here, and then next lecture will be discussing more details about this condensation heat transfer conditions, and different problems will be taken up to discuss or apply the same thing. Thank you very much.